Hello everyone. In this video we are going to talk about two of the GD&T symbols that I have not discussed in my previous video: maximum material condition MMC and least material condition LMC, and they are shown by M and L inside the two circles. So what is the maximum material condition? What is it? So it's the maximum amount of material that something has, as the name says. So if the part is like a shaft, right, then the maximum material is going to be what? Is going to be when it is made to the maximum size of it. So if it has some upper limit and lower limit, of course, when it is made to the upper limit, that is its maximum material condition. On the other hand, for a hole, it's MMC when the hole is the smallest, which means the minimum amount of material is removed, so it's the maximum material left for the part. So for a hole, the maximum material condition will be the minimum size of it. For a shaft, it's going to be the maximum size of it. Okay? So they are different from each other, MMC for a hole and a shaft. Now, when is it that MMC is useful? So if you want to have two parts to have a clearance fit, or they always have a gap between them, or the parts can go inside the other one easily without any friction, without any force, and gets out, right? So it's loose fit, what we might call. Then MMC is useful. How? Here, if you make sure that the MMC of the shaft is always less than the MMC of the hole. What does that mean? It means the largest size of the shaft is still smaller than the smallest size of the hole, right? So you made the hole the smallest, you made the shaft the largest, but still that largest shaft is smaller than the smallest hole. Still the shaft can go in and out without any problem. Then you definitely have what? Clearance fit. So for clearance fit, the MMC of the shaft has to be less than MMC of what? The hole. Then you assure that you have a clearance fit, right? Or no interference, you might call. And the way that you check it is by what? By what we call a go gauge or a go pin. So let's say in this case, I have a hole with a diameter of 10 plus and minus 0.055 and negative 0.095. So what is the smallest size here that the hole can have? What is the MMC for the hole? Well, it's its minimum size, which is what? It is going to be 9.905, correct? So the minimum size is 9.905. So what would you do? You make a pin that is a little bit, very, very little bit less than the minimum size of this hole. So if this guy is 9.905, this guy is 9.900. So it's only 5 thousandths less than the minimum size. And if this go pin can still go through the hole, then I'm saying that the hole is what? In spec, right? Because a pin that was very, very close to its minimum size can still pass through, and so this hole cannot be any smaller than that. On the other hand, when we talk about the least material condition, the least material for a shaft is, of course, its minimum size, minimum diameter, and for the hole, the least material is when you remove the max, so it's going to be its max diameter, exact opposite of previous one. And when is it that LMC is good? LMC is good when you want to make sure you have a press fit, or what we call an interference fit, or a snug fit. There is no gap whatsoever, and you have to use heat treatment, and you have to use a lot of force to insert the pin into the hole, and you cannot easily get it out anymore. Okay, it's a very, very snug fit. How would you ensure such a thing? Well, in this case, you make sure that even if the shaft is made the smallest and the hole is made to the largest, still that hole is smaller than the shaft, or the shaft is larger than the hole. So the LMC of the shaft, this case, is bigger than the LMC of the hole. Then the fitting is absolutely a press fit or an interference fit. How would you check this? How would you check whether the hole is in spec or not? The way you do it is, this time you create a pin that is slightly bigger than the maximum size of the hole. So the maximum size of the hole in this case is 10.1. This guy is 10.102, so it's only 2 thousandths bigger than what? Here it says 2 microns, but actually it's 2 thousandths. Okay, unless this is 10 mils and we are talking about micrometers, then yes, that's right. So if this is mils and we talk about micrometers as it says here, and this is mils, then yes, that 2 thousandths of a millimeter means 2 microns or 2 micrometer, which is correct. So that is the difference between the size of the shaft and the size of the hole. And the shaft is a little bit bigger than the biggest size of the hole. So if I want to assure I have a press fit, this shaft should not pass through the hole easily. As I said, it needs heat treatment. So if I don't use anything, this pin should not pass through. So we call it a no-go pin or no-go gauge. So if it doesn't go through that, then I say the hole is what? In a spec. So this is for what? This is for the diameter only. That we talk about MMC and LMC. But MMC and LMC are not only used for linear tolerances. As we said, these are also for geometric tolerances as well. So on which one of those geometric symbols that we learned in the previous lecture, right? Out of these guys, which one of them do we use that MMC and LMC for, right? Only 4 of these can come with LMC and MMC, and the question is which ones? And the only ones are straightness, flatness, perpendicularity, and the true position. These 4 can also have MMC and LMC, and in those cases, what do we call them? We call them modifiers. So LMC and MMC for them are called modifiers. Now let me tell you what that means. But before that, I need to talk about what we call rule number 1 of GD&T, or the envelope principle. So let me explain that, and then we're going to see different scenarios for modifiers like MMC with straightness, with flatness, and so on and so forth. So let me first explain the envelope principle. What does that mean? Let me read it and then I explain it. It says, when only normal dimension tolerances of size are applied to the part, the variation of the size and the geometry must not pass or extend beyond the dimensional tolerance zone. Well, what does that mean? So here, let's say I have a cylinder, a shaft, with a diameter of 10 plus minus 0.1. So the maximum size I can have is 10.1. The minimum size is what? 9.9. Fine? Good. So if I machine my shaft between these 2 diameters, tolerance-wise, linearly, in terms of linear tolerance, I am in a good shape. But assuming what? Assuming that this shaft is made perfectly straight and the surface is perfectly what? Mirror, like very smooth. There is no up, there is no down, and also what? The cross section of the shaft is a perfect circle. So there are so many things that can go wrong. Right? The surface does not have a circular section. It has ups and downs. The axis is not bent, and so on, which we know them by straightness, by circularity, and by what? By the straightness of the axis. So here I want to talk about one of these scenarios, and that is when the cross section of the machine part is not perfectly circled. So I'm talking about circularity here. It is made a little bit elliptic like this. Now my question is this: how far can this shaft deviate from a perfect circle, and how elliptic or different from a circle can it be depending on what size it has been machined? So the answer is this: if the shaft is made exactly to its maximum size of 10.1, so the shaft is made perfectly at the largest size, can the shaft have a different cross section other than a perfect circle? Is that a possibility? And the answer is no. Why not? Well, let's take a look. So here I create a shaft that is 10.1, like this, the biggest size, but then I distort it and I make it a little bit elliptic like this. Well, what can happen here, as you can see? As you can see, now this non-circular shaft at maximum size of 10.1 is now going to be in one direction bigger than 10.1, right? And this is not acceptable. On the other hand, if I go ahead and make it the smallest size, which is 9.9, like this, and again, what? Again, I make it non-perfect. I take it out of circularity position and make it a little bit elliptic. Then what happens? Then again, in this direction, in this horizontal direction, this shaft is smaller than the minimum size. So you see, this guy does not fit, and the other one that was at 10.1 and it was non-circular, that also doesn't fit. So when I am at the extremum conditions, minimum or maximum, LMC or MMC, then I cannot have geometric deformations like form deformations, angle deformations, parallelism, perpendicularity, any of those that are violated, circularity in this case. It means I will get out of what we call an envelope. So here the envelope is what? Is this disk, which is between 9.9 and 10.1. The cross section should definitely fit between these two circles inside this ring. Now, on the other hand, this is the envelope principle. But on the other hand, if this shaft is not made at 9.9 or 10.1, it is made somewhere in between. Like, for example, this guy here, this red one, is probably like 10 or something. When it's 10, can I have some deformations in the shape like circularity? Can I have it to be not perfect? Yes, I have some room because I'm still within the envelope. Okay, so now with that in mind, let's go ahead and look at some of these scenarios where I add a modifier to a geometric tolerance at the same time and see what happens when I combine my linear tolerance with geometric tolerance and a modifier, see what that means. How do we interpret that? So here we look at the straightness for the median line of a cross section with a modifier m. So like what? Like here I have the cylinder, and I say the cylinder has a diameter of 10 plus and minus 0.05, and the median line has to be straight with a geometric tolerance of 0.03 with a modifier m. Well, what does that all together mean? Well, let's take a look. So how do I interpret all of this information? The top part is easy. The top part means the shaft can be between 10.05 and 9.95, these two numbers. That is very easy. Now, what does this bottom part mean? It means that when the shaft is made at the maximum material condition, when is it that it's maximum material? You know, shaft is maximum material when it's the largest diameter, which is 10.05. So at 10.05, the amount of non-straightness, the tolerance zone for this median line for not being straight is only what? 0.03. What does that mean? Means if I have the theoretical median line, and if I draw two lines parallel to it, where the gap between these parallel lines is 0.03, then any point of this bent median line, which is not straight anymore, any point of this bent median line should fall inside the tolerance zone. Okay? So all deformation I can have, all bending I can have in this axis is only 0.03. Gap of 0.03, nothing more when my shaft is made to the maximum size. On the other hand, if I deviate from this 10.05 and I make the shaft smaller all the way to its minimum size, as I drop the size and I make it smaller, can I change this gap? Am I allowed to have more bend for the median line? Because the shaft is smaller, can I have a bigger tolerance zone for the bending of the non-straightness of the median line? The answer is yes. How much more? As much as what? The difference between the current size and what? The MMC. So if you go all the way down to LMC, how much is it? Is 0.1. If you go down from this number to this number, reduce the diameter by 0.1, then that 0.1 is going to be added to the tolerance zone. So now your allowable tolerance zone for the bending of the median line is what? 0.13, which is that number plus 0.1. So this extra amount of geometric tolerance that you gained because you are deviating from the MMC value, this amount is called the bonus tolerance. And why can I do that? Because of this previous one, the envelope principle. So the question is, what is the envelope of this part at the moment? If I don't add this geometric tolerance at all, right? So for a moment, let's say that I don't have this geometric tolerance, okay? I don't have this thing. Then the question is, what is your envelope right now? So I don't have that, okay? What's the envelope? The envelope is, if this is 10, I can add plus and minus 0.05 to it. So the largest size I can possibly have is 10.05, right? 10.05 is the biggest thing, which right now I can get it by what? At MMC, I can draw a tangent line here, right? Let me bring it down between that tangent line and another one down here like this. So this is the biggest volume, the biggest envelope that I can fill. Between that red line and this red line, the total distance is what? How much is it? It is 10.05, which was initially, and then I have an extra 0.03 of deviation, right? So what is it? It is 10.08. Let me add one more line and then show you the numbers here. Here, now you can see it better. So this distance between this red line and this red line is 10.05, the maximum size that I had. And then I had some bending allowed of 0.03, so that gap is the same as this one, right? That's the biggest gap that you can have. So the total size of the envelope in this case is what? 10.08. Yes? This is the biggest envelope that you can fit your part in, 10.08, the sum of these two numbers. Now, if on the other hand, I make what? I make this shaft, this dimension, I change it, and I make that 10.05 to go down to what? I make this guy to go down to 9.95. Since the sum of the two is fixed, right? The sum of the two is fixed. That makes this 0.3 to go to what? To 0.13. Because now sum of this number and this number is the same as sum of this one plus this one, and that is what? The size of the envelope. Yes? So this is what we call a bonus tolerance. The shaft is smaller, it can be bent more, and it can still fit inside the box. Which box? The box that has a total height of 10.08. That's the envelope, the box. Another example. Let's talk about flatness here. So if this is a box, basically, and this dimension is 10, and we say I want the median line, the median plane in this case, not line, because it's flatness and flatness is 3D, so we are talking about median plane. I want the median plane of this box to be flat with a tolerance zone of 0.03 at MMC. What does that mean? It means, hey, if I make the biggest box possible with a height of 10.05, still the midplane can be bent for a gap of 0.03, so the maximum height that I need to put the entire box in is going to be what? 10.08, which is the MMC value, which is 10.05, plus the tolerance zone of 0.03. This is the size of the box that I need to keep this object inside. Now, if I don't make my box as tall, if I make my box just 10, not 10.05, just 10, can I have the middle plane a little bit more bent? And the answer is yes. Because now this guy is not at MMC, this is only at 10. So this bending can be what? Can be 0.08 instead of what? 0.03. Like that, huh? This total size of the envelope or the box is fixed. My size is now 10 instead of 10.05. And so I can have more bending in the part. So this extra 0.05 that I gained for the bending, that is what we call, which is the difference between these two numbers, is what we call the bonus tolerance, the bonus geometric tolerance, because my linear dimension is not at MMC. Let's look at another scenario. The position with the modifier. So here, let's look at this. How do we interpret that? Here I'm saying the diameter of this hole is 10 and it can be made plus and minus 0.05 bigger or smaller. I'm also saying that the true location of the center can be off radially by 0.03, where my datums A, B, and C, which are the bottom, the right, and the front face of the object, are to be fixed on the table, on the inspection table. Good? Fine. Now, how do I check whether I receive something, and I want to know whether this part that I received is in a spec or not? How do I inspect it? So the part that I have in this case is an external feature. So it's this top part here, this guy. This is the part that I have. this plate with that shaft, right? So my question is this: what is the size of the hole here on the inspection table that I should have, so I ensure that this pin here goes what? Goes through that hole, and if it does, it means my part is what? Is in spec. How can I do that? Well, clearly the offsets for the center of that with respect to the datum B and datum C should be what? 25 and 25, right? That's the center of that hole. But what is the diameter of that hole that you need to have in order to make sure this shaft is passing through it? Well, here it says that the gauge hole, right? What is going to be the size of the gauge hole here? This guy. It says it is the largest pin size MMC plus positional tolerance. Well, what does that mean? Well, what is the largest pin size that I can have? It is going to be 10 plus 0.005, right? That is the biggest pin that I can potentially have. But guess what? This pin center can be off from the ideal position, from the intended position, by 0.03, right? So if I look at this shaft and the hole from the top view, where the red is the shaft and the blue is the hole, correct? This center here is what I want to have, true position, right? But this red one is what? Is the shaft. And the center of it is off, and this off here, this offset is 0.03. So how big can I have this? Should I have this? Well, if this guy is 10.05 and I have offset of 0.3, then the diameter of this should at least be 10.08. If this guy is 10.08, then with a 10.5 diameter and a 0.03 offset, the shaft will always pass through the hole. Right, so you see it says the gauge hole diameter is equal to the largest size of the pin plus the positional tolerance. On the other hand, if I want to what? If I want to basically inspect a hole, not a shaft on the part, I want to inspect this hole. This time my inspection table has the shaft. So this time the shaft is on the inspection table and the hole is on the part. The question is this: what size of pin do I need on the inspection table this time? So again, this shaft can pass through that hole where I fix datums B, C, and A. Well, how do I get that? It says the gauge pin is equal to what? The smallest hole size minus positional tolerance, for the same reason that the shaft should pass through the hole. So, if I want to ensure passing, I have to consider worst case scenario where the hole is made the smallest, and I have to consider that the center of the hole and the center of the shaft are off by 0.03. So if I subtract that 0.03 from the size of the hole, the minimum size of the hole, which is MMC of the hole, that is going to be the size of this pin. Then I'm sure that it can pass through. So you see, this MMC can help you. This MMC, this geometric tolerance, and the values for this linear tolerances for the hole or the shaft, they help you design what? Design a pin or design a hole on what? On the inspection table. And if it passes through, the shaft passes through the hole, then the part is what? In spec. The last example, perpendicularity of an axis with a modifier. So here you are saying that this shaft, this hole is made with diameter 10 plus minus 0.05, and the axis of this hole has to be perpendicular to the top face A at MMC with an offset of 0.03. Well, what does that mean for us in terms of the inspection? Because if I want to check whether this part is made to the spec, I need a pin, and that pin has to pass through the hole to ensure that the part is in the spec. The question is, what is the size of the pin that I have to consider in this case? What size of the pin should I consider? And the answer is this. If the hole was made perfectly perpendicular to A, perfectly perpendicular, then what is the size that you need for the pin? Well, it has to be at or equal to what? To the least material condition, to the smallest hole, which is 9.95, right? At 9.95, or a little bit, a few microns less than 9.95, the shaft will pass through the hole. But now the axis of the shaft hole is tilted. It's not completely perpendicular to the top face A. And how far can it be off? Well, the amount of being off is what? How much is this off? Is 0.03. So from the bottom point here of this axis to the top point of the axis, this amount of vertical deviation is 0.03. So that 0.03 should also come off 9.95. And that is going to be the size of what? The pin, right? That is going to be the size of the pin. Let me add some arrows for you here so you can see it. Okay, now you can see it better. So this dimension from this point here to this point there, that's the diameter of the hole, the minimum, which is 9.95. And this deviation here is 0.03 because of the tilt of the axis. If you subtract this 2, then the diameter allowed for the pin should be what? 9.95. Right? So if you want to design a pin, the size of the pin should be 9.92, sorry, 9.92, not 9.5, 9.92. If you design a pin like that, it should definitely, under all conditions, should pass through the hole in the part, even if the axis is tilted, and if it does, that means the part is in spec. So you see that by adding a modifier, the sizes of the pins or the holes that we use for inspection are affected, and also what? The amount of the geometric tolerance that I can have is also what? Affected. I get something called bonus tolerance. That's why we call this M what? Or L, we call it a modifier, because they change how we can interpret and how we can inspect geometric tolerance. The last thing I want to say is that we call it rule number 2 of GD&T, regardless of feature size, or RFS, which says regardless of what size you make the part, the geometric tolerance is not going to be affected if you do not use any modifier. So if you don't see M or L, then whatever geometric tolerance is provided, that is going to be fixed, and that does not depend on which size between the upper and lower limit you are going to manufacture the part. There will be no bonus tolerance, basically. So if I go back to that flatness example, and if I get rid of that M, I just say the median plane is flat with a tolerance of 0.03, then this relation, which is sum of the MMC and sum of the flatness is 10.8, that is not going to be there anymore. So if I make my if I make the dimension, not the diameter, make it, because that's a H in this case, let's call this H. If this H is made exactly 10, what is going to be the tolerance zone here, right? How much is it if I make it 10? Remember, if I made it 10.05, it was 0.3. If I made it 9.95, it was 0.13. And if I made it 10, it was 0.08. So what about this case? If I make it 10, which is the mid-range, how much is the tolerance zone? Guess what? No difference. It is always going to be 0.03 because there is no modifier. Okay, so it is going to be 0.03 regardless of what? Regardless of the size of the part. So here I fix it. This is H, not phi, because this is not a diameter. So, and if I made it 9.95, still the same. If I made it 10.05, the same. This number is not going to what? Change, and so we call it regardless. We call geometric tolerance regardless of what? The feature size. What's good about this? Why should or should we not add a modifier? We learned why we should add a modifier, right? Because, for example, we want to have interference fit all the time, or clearance fit all the time, or anything for that matter. But why is it that we should eliminate these modifiers or not use them? Because we want to have a balance, and we want to make sure that the geometric tolerance is not impacted by your manufacturing size to be on either side of the nominal dimension. If you go above it or go below it, none of that is going to affect what is going to affect your geometric tolerance, and it is maintained independently. Okay, so depends on how much this curvature is important to you. If you really do not want more bending than 0.03, if you do not want to allow more bending than that, then do not add a modifier. If this bending is not super important to you, the overall height is important, the size of the envelope is important, then go ahead and add the modifier M. Okay? So it depends on whether here the bending is important or the size is important. Then you can add or not add a modifier. So hopefully this video was useful to you and I could clarify a little bit about these modifiers, and I'll see you in the next lecture. Thank you.